All right. You
Hey,
there, Gerald?
Richard, I'm
There you are.
here. You're there in infrared.
Yes, I'm here in infrared once again. And just to prove that I'm still alive. The I gotta say, for those who are watching tonight, you're clearly not baseball fans.
Yeah, really.
So I
And
had
and
tickets. I had
and
tickets to this game, Gerald, and
oh,
these are the things I do for astronomy.
yeah, really. Okay, so don't anybody tell us the outcome of the game before this is over. Because I'm gonna go home and watch it. I'm recording it, so I
Uh,
want I want to go home and watch it.
we won't
So
ruin it for you, and I will ask John, who I know is watching us, but is also across the street from Pac Bell Park, not to not to tell
hey,
us
hey
the score.
Richard, they don't. It's now Oracle Park. Went from
Oh, is it really? I didn't know
Yeah, it
that.
went from
See, there you
Pac-Bell
go.
to AT&T to Oracle.
Well, I'm in denial.
So well, anyway, welcome everybody. This is the Chabot Space and Science Center virtual telescope program. We're coming to you from up here at the Chabot Space and Science Center. Behind us is the 36-inch reflecting telescope we call Nellie. And we've got a camera mounted on it. We've got clear skies. We've got a little bit of turbulence tonight, so the scene is not perfect, but we will be able to look at a number of things tonight. Um, just want to remind everybody the Chabot Space and Science Center is still closed to the public, although we are getting closer to our reopening date. We will be reopening on November 12th. In the meantime, we are doing lots of refurbishment in the inside of the facility. We've got some new exhibits. We've got new staff, new volunteers who are being trained. So lots of things are going on up here. And since we aren't open to the public, the revenue situation isn't ideal. So we do ask that you take a moment to help us out if you can. You should, if you're on Facebook, you should see a donate button somewhere on the page there. If you want to click that and make a donation, we would appreciate it. If not, you can go to the Chabot Space and Science Center website, which is chabotspace.org. And when you get to that web page there, you'll see a donate button at the top of the page. Just click on that. Help us out. We appreciate it. All right.
Great, thank you.
Okay. So I want to start. We're on both YouTube and Facebook, and I saw a question that came up on YouTube, and I wanted to answer it real quick. Somebody asked about the eccentricity of the Earth's orbit and whether it's increasing. And in fact, the Earth's orbital eccentricity changes continuously. So very quickly, what we mean by eccentricity of the orbit. The orbit around the sun, the Earth's orbit around the sun is not a perfect circle. It's a slightly flattened circle. And the amount of flattening of that circle is measured by a parameter we call eccentricity. A perfect circle has an eccentricity of 0, and a perfect hyperbole has an eccentricity, or actually a perfect parabola has an eccentricity of 1. So typically orbit eccentricities are somewhere between 0 and 1. The Earth's eccentricity is almost 0, but not precisely 0. It ranges between 0 and about 0.06. So it is just very slightly out of round. And it changes over time, and it increases and decreases over long periods of time. And I think there's actually 2 or 3 different cycles involved with it. I know one of them they call the long cycle is 400,000 years. And then there's a couple of short cycles. One of them I think is 96,000 years. I forget what the other one is. But anyway, the eccentricity does change over time. So the answer to your question is yes, it is changing. I'm not sure whether it's right now it's in the increasing or decreasing mode, but it will change over time. And I hope that answers your question. All right.
Great.
So how about if we look at a couple of planets, Richard?
I think that's a great idea.
All right. Well, we're kind of close to Jupiter. You want to switch over?
Yeah, let me go ahead and
All right.
share the camera software.
So we have a camera mounted to our telescope, and in just a few seconds here, we're going to share with you the view that that camera is seeing through the telescope. So we are right now on just a star that we use to synchronize the telescope, and we're going to switch to Jupiter here in just a second. Here we go. This telescope is computer controlled. So you'll hear us talking periodically about readjusting the telescope and getting it onto a certain object. Looks like we're out of focus there a little
Oh
bit.
yeah, we got all kinds of adjustments we got to make here. First thing let me do is get the exposure right and get rid of all these boxes and circles and arrows. And we'll zoom in a little bit. And we can then, let me play with the focus.
Yeah, I tweaked it a little bit already.
Oh, do you want to give it a shot since you're looking?
Yeah. Can you go a little brighter so I can see one of the moons? It's easier to focus on the moon.
Oh yeah, good idea. All right, I'll put it on a 20th of a second. There you go.
All right, I don't see any moons.
You should see them pop up right here, and if not, I'll grab the focus paddle.
Yeah, I don't see them.
Okay, let me go ahead and do the focus then.
Looks like we're pretty close already on the focus.
Yeah, I just made it better. So.
All right. Okay.
Let me go down to 125. There we go. Maybe make it a little bit brighter.
So this is the planet Jupiter. Jupiter is the the fifth planet from the sun. It's the biggest planet in our solar system. Jupiter is 11.2 times the diameter of the Earth, so it's about 88,000 miles across. Jupiter is a gas giant, so it is mostly a lot of very dense gas. It does have a small solid core at the center, but between there and what you see there at the surface, there's a whole lot of gas. It's mostly hydrogen gas, but there's some helium and some methane and a few other gases, carbon dioxide and so on. Jupiter rotates very rapidly. It takes about 9 hours and 55 minutes to make one rotation around its axis. Compare that to 24 hours for the Earth. Now, if you think about that, you've got a planet that's 11 times bigger than the Earth, and it's rotating, makes one rotation in only 9 hours and 55 minutes. So you can imagine that at the equator, things are moving pretty fast. And Jupiter's atmosphere has high and low pressure areas, just like on the Earth. But with that very rapid rotation, those highs and lows get wrapped around the planet, and you end up seeing bands around the planet. And you can see a couple of them there. There's some couple of dark bands and some light bands. The dark ones we call belts, and the light ones we call zones. The belts roughly correspond to low pressure areas, and the zones are high pressure areas. Although you can't see it in this image, if we were able to do quite a bit of a close-up, you could actually see that there's a whole lot more going on than just those stripes around the planet. There's all kinds of eddies and swirls. There's the Great Red Spot. There's lots of other smaller cyclonic activity going on. It's a very chaotic place. And much of that is due to the fact that it is a gas giant and it is rotating very rapidly.
So it doesn't look like we have a view of the red spot tonight.
No, I don't.
Right
I
now.
don't see it.
I don't see it at all. And it's always a roll of the dice if you're not actually studying to see when the red spot's going to be facing you, whether or not you'll see it when you just point a telescope at Jupiter. But
my brain is sort of telling me that on right at the limb on the right side, I think I might see it on the lower belt, but
right there.
Yeah,
I don't know.
maybe yes, maybe no. I don't know.
Maybe. Yeah, I see.
Yeah.
I know what you're seeing there. I know what
Yeah,
you're looking at, and
yeah.
it's
There's
very hard to.
something there, but there are other blotches in the atmosphere, so it's hard to tell unless it's somewhere close to the longitude that faces us.
No, it's not a bad view though.
Oh,
We're playing around with a different camera tonight. Tonight is a Canon 6D. That's a full frame camera that is pretty well known for being decent for astrophotography. And I've never tried it out on this telescope before.
yeah,
So
it actually does look pretty good. It's pretty
yeah,
steady.
yep,
So Jupiter has, I think we're up to 79 moons or some large number like that. It may be actually over 80 now. Most of them are very small moons, but there are 4 large moons around Jupiter. We call them the Galilean moons. And Richard can change his settings to bring out the moons. One of the interesting things is to compare camera sensitivity to the human eye sensitivity.
yeah,
If you look at Jupiter through a telescope with just an eyepiece in your eye, you see both Jupiter and the moons clearly and detail on both. Unfortunately, cameras don't quite have the dynamic range to do that. So we're seeing some moons. I see 3 of the moons. I'm not sure. I don't think I see the others, but
no.
Jupiter has these 4 moons we call the Galilean moons. They're relatively large moons. And they orbit around Jupiter all on the same orbital plane. And that orbital plane happens to be parallel to our line of sight. So rather than seeing the moons go around Jupiter in a circle, the moons appear to just move back and forth across Jupiter. So you see 3 of them on one side right now. Tomorrow night, you might see 1 or 2 of those on the other side. And over time, they just seem to move back and forth along a line that bisects or crosses Jupiter. Sometimes when they are in front of Jupiter, in front of it being on the sun side of Jupiter, one of the moons can cast a shadow on Jupiter. And then when the viewing conditions are really good, we can actually see the shadow on Jupiter as well. There's an interesting thing that I wanted to share with you, if you give me just a couple of seconds here.
Yeah, go for it.
Those 4 Galilean moons have an interesting property in their orbits. When we talk about orbits, a lot of times when you have more than one object orbiting the same parent body, the orbits get into what's called mean motion resonance. And in mean motion resonance, the orbit of the inner object will be some whole number increment of the orbit of the outer body. And that's true with the orbits of Jupiter. And so I just wanted to kind of share with you some of the interesting data. The closest of the 4 moons is Io. And Io takes 1.77 days to orbit Jupiter. So less than 2 days, Io makes one complete orbit around Jupiter. The next moon out is Europa. Europa takes 3.55 roughly days to orbit Jupiter. Well, 3.55 is approximately exactly 2 times 1.77. Within a couple of hundredths, it's 2 times. So we say that Europa and Io are in a 2-1 mean motion resonance, meaning that for every 2 orbits of Io, Europa makes 1 orbit. The next moon out is Ganymede. Ganymede's orbit is about 7.15 days, and that turns out to be about 2 times the time it takes Europa to orbit Jupiter. So Ganymede and Europa are also in a 2-to-1 orbital resonance. Now, the most distant of the 4 moons is Callisto. And Callisto is a little bit different. It takes 16.69 days to orbit Jupiter. And that puts it in a 7.3 orbital resonance with Europa. So for every, a 7.3 orbital resonance with Ganymede. So for every 3 orbits of Callisto, Ganymede will make 7 orbits. And the result of all these orbital resonances is that periodically the moons kind of line up. They're all in the same spot and in the same orientation relative to Jupiter. So, for example, with Io and Europa, Io makes 2 orbits, Europa makes 1 orbit. They line up with each other at a certain point. 2 orbits later for Io and 1 orbit later for Europa, they arrive at exactly the same spot, and they're once again lined up. So that's what happens with mean motion resonances. And those mean motion resonances are actually very common. There are a lot of moons in other planetary systems that do the same thing. So we encounter it quite often, and it's just very interesting to see how that works out. It's some sort of gravitational interaction between the moons that causes them to fall into these resonances.
So, well, there's a lot of examples of resonance, and it's always because of the type of interaction you're describing. Even musical instruments, of course, have resonance, and it's from the frequencies of the individual strings, for instance, on a string instrument, that will create that type of resonance, and also the frequency of the sound producing portion of the instrument with the body of the instrument. So it's not a different phenomenon. It's just a different example of the same phenomenon.
Another good example is Neptune and Pluto. They are in what we call a 3-2 mean motion resonance. So for every 3 orbits of Neptune, Pluto makes 2 orbits. And so again, they line up with each other periodically in the same spot relative to the sun. So very common phenomenon, and it's interesting to see how often we encounter mean motion resonances in astronomy. All right.
Yeah, good explanation. All right. Well, since we're in the neighborhood there, why don't we move over to Saturn?
All right.
And I'll zoom back to our
I
size here.
I want to do just a small change. There we go. And sync that. And head on over to Saturn. Okay, on the way.
Okie dokie. All right, there it is. Just need to center it for us a bit, and I'll brighten it up.
Yeah, I'm seeing some disagreement here about mean motion resonances. I got somebody on YouTube who says Pluto is not in a mean motion resonance, but yeah, it actually is. It's in a mean motion resonance with Neptune. It's in the 3-2 resonance. There are several other Kuiper belt objects that are a similar semi-major axis to Pluto, and they also are in a 3-2 resonance with Neptune. And as a result, we call all of those objects that are in the 3-2 resonance with Neptune, we call them Plutinos.
Plutinos.
Yep, that's the official term for the Kuiper Belt objects that are in the 3-2 resonance with Neptune. And somebody asked, what is slewing? Slewing is a term we use for moving the telescope. When we move the telescope, when we command it to go to another object, it's computer controlled. The computer sends commands to the motors, which move the telescope to the right coordinates for the next object. So we just did a slew from Jupiter to Saturn. So when you hear us talk about slewing, we're talking about moving the telescope. And there are fast slews and slow slews, and we can do it differently depending on whether we're making big moves or small moves or little adjustments. So I see Saturn. I see rings.
Do you want to see if we can catch any of the moons here?
Yeah.
Let's see if we are able to do that. Put it down at a 60th of a second. I am not seeing moons.
Should be able to see at least Titan.
It may be out of the field. That's the only thing I could think of.
Yeah, that could be.
When it's furthest from the planet, it tends to be pretty way out.
Yeah.
So anyway, we're not seeing
moons tonight. That's unfortunate. Titan is a very large moon. It's one of the, in fact, it's basically the only moon that has a significant atmosphere. Titan has an atmosphere that's a lot of nitrogen and methane and ethane. And it actually is kind of in a state of permanent smogginess because of all that methane. So it looks kind of cloudy there. And the methane, because it's so cold there, the methane can actually condense out of the atmosphere and rain. And the surface of Titan is mostly water, water, but it's in the form of ice. And it's very, very cold. So that ice is literally as hard as a rock.
Well, it also has sizable methane lakes.
Correct.
Because that methane that precipitates out of the atmosphere pools up and creates some fairly large bodies of methane. And methane lakeside property is going very cheaply.
Yeah, actually, if you look at pictures taken by the Cassini spacecraft or the Cassini-Huygens spacecraft combination, you see that there are actually rivers and streams and lakes, like Richard says, and it's all liquid methane that is flowing. Like I said, it rains and it runs down the hills and into the streams, and the streams run into lakes. It's pretty amazing. But at those cold temperatures, water ice is literally as hard as a rock.
Wow.
All right. So, yeah, Titan is the biggest of Saturn's moons. It's quite a bit bigger than any of its other moons. So there's a significant difference. It's not like Jupiter, which has 4 pretty big moons. Saturn has 1 big moon and then a bunch of smaller moons. Rhea, Iapetus, Dione, and Tethys are examples. But just to give you an idea, Titan, the biggest moon, its radius is 2,575 kilometers. The next biggest one is Rhea, and its radius is only 763 kilometers. So huge difference between Titan and all the rest of the moons.
So Kramer asked, does methane in a lake have similar properties to water? That's a pretty interesting question. It's certainly more volatile, but it is forming a lake. I imagine you could I wonder if you could put a boat on it.
Well, let's go there and find out.
Or would it, or would the methane be lighter? And
Yeah, it'd be interesting to find out what
yeah,
that would be like. Yeah, yeah. So the answer really is we don't know for
we don't
sure.
know.
It's a liquid, so you gotta think it behaves like a liquid, but it might be a much lighter liquid, so tends to slosh around a lot easier or something like that. I'm
Yeah,
just guessing.
yeah. He
So
wants to go methane skiing now.
yeah.
Well, I imagine also you don't want a methane lake where you have a high oxygen content because that sounds like a rather explosive situation.
Yeah. So on YouTube, John asked why don't there are lightning strikes on Titan. Why is it that those lightning strikes don't ignite the methane? Well, as you guessed,
like I said, no oxygen.
No
right?
oxygen, right?
Yep.
So you need an oxygen or some oxidizer in order to get some kind of a burning or explosion or what have you, and it's not there, so you don't get it.
All right, we're getting some pretty funny comments on this. Right? All right.
Okay.
I think it's time to move to some deep sky objects.
All right.
We kind of missed out on that last week for the most part because we were enjoying the planet so much. So how about M15? It's well positioned, and when we start moving the telescope, we could tell people exactly what that is. You're always going to hear us talking about M this and M that, M1, M2, all the way up to M102 or M104. And the M stands for Charles Messier. He was a French astronomer who lived in the 1700s and started the famous Messier catalog, where he would learn about objects, mainly objects that were not comets, because what he was really interested in doing was finding comets. But anything he stumbled across that was not a comet, or anything that had been recorded by his colleagues or previous astronomers that were not comets, he decided to put in his catalog. And when he finished his catalog, astronomers for the next 150 years or so continued to add to the Messier catalog. And I think the most recent Messier object was added as recently as like 1945 or something like that. It was very recent. But that's what we mean when we're saying we're going to M15 or M31 or something like that. So what we're going to look at now is a globular cluster called M15, and a globular cluster is a very large number of stars, hundreds of thousands of stars that are gravitationally bound to one another. And there are several hundreds of these globular clusters in our Milky Way galaxy, and some of them are quite bright, and this is one of the brighter ones. Let me know if you're at
we're there. We're there.
Okay, so what I'm going to do is switch over to imaging, and what we'll do is take a maybe a 20-second exposure and see how that comes out.
Yeah, so this object is a lot fainter than the planets, Jupiter and Saturn. So we have to do a long exposure. We can't do a live view image. We have to. Richard's doing a 20-second exposure here.
Yeah, and we'll see if we actually have it. Play the Jeopardy song.
And who will be the host for Jeopardy?
Gerald will. Okay, we're getting close. Well, it's down here at the bottom. So
yeah. So let me do some slewing here. All right, try it again.
All right.
So as Richard mentioned, this is like a ball of stars out in space. It has about 450,000 stars in it. Those stars orbit around the center of the cluster in highly elliptical orbits. And if you recall, remember we said something about ellipses and eccentricities and all that. Elliptical orbit is an orbit that has a fairly high eccentricity, so it's very much an oval. And well, we got closer, but didn't do much.
You made a little bit of progress there.
Yeah. This bigger frame field of view is
You're not.
messing me up here.
I know, I am.
All right, well, give it a shot.
All right. Yeah, usually we work with a camera, or when I'm doing the camera work and not Rick, usually using the T1I, which is what's called an APS-C processor. And it's a smaller chip, and so Gerald doesn't have to hold the button down as long to move objects across the frame.
So anyway, the stars in the cluster are orbiting in these highly elliptical orbits. When they're in close near the center, they're moving very rapidly. When they're out towards the fringe of the cluster, they slow down, and eventually they get so slow they can't go out anymore, and then they swing back in, come back in towards the center of the cluster. Near the center of the cluster, stars are very close together, much closer together than the stars around our sun. Just to give you an idea, the closest star to our sun is 4 light years away. If you had a space 100 light years across and you were spacing stars at 4 light years between them, you'd only have 25 stars. But here, in a space of 100 light years, you have thousands of stars. So you can imagine that means they are much closer together. In fact, if you lived on a planet orbiting one of these stars, you wouldn't have a nighttime because there'd just be so many stars in your sky so close to you that they would just light up your sky. You'd probably know the difference between day and night, be a little bit dark, but not totally dark at night. Now, this particular globular star cluster is what we call a core collapse globular cluster. So it's very much concentrated near the center. And when we do the math, when we calculate how much mass should be within the central, say, 10 light years of this cluster, it turns out it's a lot. So much so that we're fairly certain, I'd say 90% certain, that there is an intermediate mass black hole at the center of this globular cluster. And it's likely that there are intermediate mass black holes in the center of quite a few of the globular clusters that orbit around the Milky Way. Right.
So the interesting thing about globular clusters also is the estimated age of the stars, because globular clusters consist of what are called generation 1 stars, or mainly generation 1, some generation 2 stars, but they tend to be very primordial and they tend to be very old. So the majority of stars in these globular clusters are older than 10 billion with a B years old. Some of them as much as 13.5 billion years old, which is getting to the estimated age of the known universe. So these are a way for astronomers to study some of the conditions that were in place when the universe was just forming. And it's also a way to contrast stars in the early universe with newer stars that have heavier elements. And we're able to see the difference between these old stars and newer stars by studying their spectra and the absorption lines and emission lines from stars that are old differ considerably from those that are new. And you can then see how elements that are formed in stellar evolution end up getting captured by the newer populations of stars and ultimately become part of the planets that orbit those stars.
Yeah. A lot of the chemistry that makes up our bodies was made in later generation stars. Um, these first generation stars are mostly hydrogen and helium, and they don't make very much of the other elements. And so when you, like Richard says, when you analyze these stars spectroscopically, mostly what you see is hydrogen and helium. You don't see heavier elements like iron. You don't see things like phosphorus and so on and so forth. But then when you look at newer stars, they have those heavier elements in them because those heavier elements are produced by supernova explosions, neutron star collisions, and so on. And they sort of seed the galaxy with all those heavier elements. But
That's right. If it wasn't for supernova, we wouldn't have elements like gold and uranium and all of these elements that are heavier than iron. Everything would just stop at iron, and that would be it.
yeah, Richard, there are a couple of questions that come up on YouTube that I think we should address. One of them was someone asked if we could explain what we mean by the difference between long exposure and live viewing or live
Oh,
stacking.
sure, sure. Okay. So when when I'm taking an exposure like the one you see right now, I'm keeping the shutter open for, let's say, 20 seconds in this case, and it's collecting all of the light from the 20 seconds onto one quote unquote frame, or one area of memory, and then saving that as a single image. If this was an older style film camera, it would be like having a piece of film in the camera, opening the shutter for 20 seconds, closing the shutter, developing the image, and saying, okay, this is what 20 seconds looks like. When I'm in live view, like we were with Jupiter and Saturn, what it's doing is more similar to a video camera. And what it's doing is taking a whole series of very short frames so you can see what's going on live. And that's really not designed for astro cameras or astrophotography as much as it is for people who like to have a DSLR pointed at an animal at the zoo, see it walking around when you're looking through the back of or looking at the back of the camera on its LCD screen, and saying, that's when I want to take it. So live view actually shows you the image as it appears through the lens. And we leverage that on our program here to look at the brighter objects. It tends to work really well with bright planets, and it works great with the moon. So, in fact, we should talk about this for a second. Next week, we're going to be spending quite a bit of time talking about the moon, looking at the moon, and we'll be doing a live view of the moon because it's such a bright object. I just have to have the camera in that video mode with maybe 125th of a second frames or 200th of a second frames going continually as we see it through the telescope live.
Yeah.
And I hope that explains it. That's the difference.
Yeah. One other thing that I want to explain, though, um, in live view, which is, as Richard said, it's kind of like with a TV camera, or with if you take your smartphone, you hold it up and you're trying to get everything focused and everything, and people are moving around all that. You're seeing live action, and it's just taking one frame after another and showing you those frames in rapid succession. But there's another thing we call live stacking or just stacking, where we take all those frames, we save them, and then we go through and pick out the best of them, and then we electronically stack them to produce a much richer, deeper image that shows a lot more detail, shows more color, and that's by taking those live view frames, saving them, and then going back and electronically stacking them to produce a much better image. Some of the best quality amateur photography that you see, amateur astrophotography that you see, is done that way. They literally shoot video through the telescope and then go back and extract individual frames from all the saved images, and they extract the best ones, stack them together to produce those really high quality images that you see.
I want to show an example of this real quick. It happens to be that one of our viewers, Rich Navarrete, who is a regular participant in this program, sent me a Milky Way photo he shot, and I am going to use this as an example. So this is a Milky Way image. I'm not sure where he was. I think he was in the northern Sierras somewhere. But it's 5 20-second shots stacked in order to increase the amount of signal for producing this image. So this is an example of a stacked image. Now, you know that if you took a video camera and aimed it at the Milky Way, none of your individual frames would show much of the Milky Way or any of the Milky Way. You would have to collect, literally thousands and thousands of those frames in order to get something that resembled the Milky Way. Now, these are 20-second frames, each one 20 seconds long. And if he had gone ahead all night and done, hours of these 20-second images, then he would have been able to produce even more detail and more resolution if you magnified the image and zoomed in. So that's kind of an example of stacking and the kind of results you can get. And this was done just with a standard DSLR camera.
Yep. All right. Well, where should we go next?
Do you think we can jump over to the cat's eye? It's not that far from where you are.
Well, let me just ask the computer.
Ask Mr. Computer. I think Margot wanted to know why it stops at iron. So the fusion in a star is produced by the gravity in the star and the compression of all of these materials that are in the star. The hydrogen gets fused into helium, and helium gets fused into heavier elements, and it goes from helium to carbon to iron. Once it hits iron, there's not enough energy to produce anything heavier by gravity alone, and it's only through a supernova explosion that throws materials together at an extremely high rate that you're able to produce the heavier elements.
Well, Richard, do you have an NGC number for the cat's eye?
Let me see if I can look that up for you. It'll take a sec.
Yeah, because the computer is not recognizing cat's eye nebula. So another thing that's fairly close by is M27, if you want to look at that.
Oh, yeah, we could do that. Want to just do that?
Yeah.
Let's just do that. All right.
All right.
All right. Let me know when you're...
Yeah, it's keeps wanting to shift me to a star. So.
Oh, does it?
Yeah, well, okay, I'm going to do it the other way here. If you're going to be that way, there we go. All right, slewing. So we're going to go to M27. We should be there.
Okay.
M27 is what we call a planetary nebula. It's the remnant of a dying star. This is a star that was similar in size to our sun. It got old. When it got old, it swelled up, it became a giant star. As a giant star, it began to shed its outer layers of gas. That goes on for tens of thousands of years. It just slowly blows gas off the outer uh, envelope of the star. Eventually, that exposes the inner part of the star, the much hotter interior of the star. And at some point, the fusion process, which is the driving force of the star, stops. The star, whatever's left of the star, collapses. Looks like we need to do a little adjustment there. Huh? It's up at the top of your frame.
Oh, yeah, there it is.
So the star collapses and becomes what's called a white dwarf. The white dwarf is very small, very compact, very dense, and extremely hot. So hot that it puts out a lot of its energy as ultraviolet radiation. And the ultraviolet radiation goes out, and the white dwarf is surrounded by all that gas that was blown off while it was still a red giant. And the white dwarf puts out the ultraviolet radiation, which goes out and ionizes the gas and excites the atoms in the gas and causes it to glow. And so we see these glowing clouds out in space, and there are literally hundreds of planetary nebulae around in the night sky. And they all have a different appearance in some way or another, quite often looking very symmetrical, as this one does. It actually looked pretty good there for a second there, Richard. Yeah, you can see it as a little diffuse. This one's called M27, or the Dumbbell Nebula. It has somewhat of a kind of a dumbbell shape to it. You can see kind of the narrow neck at the center, and then on either side it flares out kind of like a dumbbell. And this is just gas that was expelled by that red giant star before it became a white dwarf. The white dwarf is the little dot right at the center. And you see a lot of color here. If you look out towards the fringes, you can see it's kind of reddish. And then as you get closer towards the white dwarf at the center, it's turquoise in color. The reddish color is caused by ionized hydrogen, actually a hydrogen that's in an excited state. It's not ionized, it's in an excited state. And when it gets excited by the ultraviolet radiation, the electron that's orbiting around the hydrogen atom jumps to a higher energy state, then it drops back down. And when it drops back down, it emits this deep red color we call hydrogen alpha. And that's the red color that you see. The turquoise color comes from oxygen. And it is truly an ionized type of oxygen, oxygen that has been stripped of a couple of its electrons. And that material, or that kind of ionized oxygen, glows under ultraviolet radiation in this very, very bright turquoise color. So the oxygen glows very brightly, the hydrogen glows very dimly. And that sort of fools you into thinking that there's more oxygen there than hydrogen, but it's actually the other way around. There's more hydrogen than oxygen. It's just that the oxygen glows a lot brighter than the hydrogen does. And there's some other gases as well, but it's mostly hydrogen with some oxygen. And I'm sure there's a lot of carbon in that cloud as well, and a few other elements as well. So this is a preview of what will happen to our sun in about 5 or 6 billion years. Our sun will eventually swell up, become a red giant. It will lose its outer layers of gas, just like the star did. Eventually, whatever's left of the sun will collapse into a white dwarf. It will be surrounded by a cloud of gas, and the white dwarf will light up that cloud of gas with its ultraviolet radiation. So this is a preview. So you don't have to wait 5 billion years to see this. You can see it now.
It's a preview, not a live view.
Right. So, all right.
Yep.
Okay,
Great,
so
thanks.
the other
So,
object we were
well, Alan did come back to us, and he told us that the cat's eye is NGC 6543, but it is in a different part of the sky from where we are now. So, your
Yeah,
choice if you want to
yeah.
move
Let's
it all
see.
the way over
We
there.
are getting
That's it.
what time is? There is something else I wanted to talk about. So if you
Okay,
don't
so why
mind, why don't
don't
we?
why don't why don't we put
Yeah,
that
yeah,
aside then? Go
yeah.
ahead.
A couple of things I wanted to talk about. Maybe we'd come out of live view here. I mean, out of screen share mode here for just a second.
Yeah.
First of all, Richard mentioned this a little bit at the beginning, and I want to emphasize it again. Next week on October 16th, it's International Observe the Moon Night. And International Observe the Moon Night is when observatories and science centers all around the world all point their telescopes at the moon and observe the moon and talk about the moon and analyze the moon and share stories about the moon and so on and so forth. We are going to do the same thing. We are going to be showing the moon. We are going to start early. Instead of starting at 9 o'clock Pacific time, we are going to start at 8:30 Pacific time, and it'll be an hour and a half long show. And the reason we're doing that is because we got a lot that's going to happen. Not only will we be showing the moon and showing you some of the lunar geography and talking about the lunar geography and so on, we are going to have some guests with us, some guests from NASA, and they will be talking about an upcoming NASA mission to the moon called Viper. And Viper is a mission to send a rover to the moon to land on the moon near the South Pole in a crater that does the bottom of the crater never sees sunlight. Because it's a deep crater and because it's right at the South Pole, the sun angle is so low that the sun never shines down to the bottom of this crater. And the reason they're doing this is to find out if there is water ice in the shadow inside this crater. There's a lot of indirect evidence that that is the case. Viper's mission is to actually go there and find out. Now, a lot of the work on Viper is being done by NASA Ames Research Center, which is right here in the San Francisco Bay Area, and Chabot Space and Science Center is partnering with the Ames Research Center and NASA. We are going to become the visitor center for the Ames Research Center. So, part of this whole partnership is we start sharing resources and things. So scientists from NASA are going to join us next week, and we are going to do a whole session just about the moon. So I want to encourage you to join us. Also, next week on October 16th, NASA will launch a new spacecraft called Lucy. And Lucy is a mission to the Trojan asteroids of Jupiter. So I wanted to take a few minutes here to share my screen and talk a little bit about the Lucy mission and what it means. I'm going to hope I get this done right here. Okay, so the Lucy mission is to go to visit the Trojan asteroids, which are asteroids in the vicinity of Jupiter. And they're in what we call Lagrange points. Different people pronounce it differently. And so I wanted to explain what Lagrange points are and then talk about what the Lucy mission is going to do. A Lagrange point is a point in space where the gravitational pull of the sun and the gravitational pull of a planet are in balance. And there are 5 Lagrange points for a planet, for example, Jupiter. And so I've got a diagram here showing you what the 5 Lagrange points are. So L1 is between the planet and the sun. It's close to the planet, much closer to the planet than it is the sun. It's a point where the sun's gravity and Earth's gravity are in balance. And if you put a spacecraft there, it will hold the spacecraft there. L2, similar idea. It's on the opposite side of the planet from the sun. And again, it's a point where the two gravities balance each other so that an object placed at that point will stay in orbit around the sun and orbit exactly parallel to the Earth. So from our perspective, it stays in the same spot opposite the sun. L2 is where the James Webb Space Telescope is going to head later on this year. L3 is a point on the opposite side of the sun, and again, where the two gravities balance. And then L4 and L5 are points on the orbit of the planet, either 60 degrees ahead or 60 degrees behind the planet. And again, it's a point where the gravity balances. Now, L4 and L5 for Jupiter are where the Trojan asteroids are found. And I got to change my display here because you're blocking my...
Ooh, me?
Yeah.
What am I blocking?
Well, I should. There it is. All right. Okay. So
I was blocking your arrow.
No, your image up on the over on the side was blocking the little arrow. Yeah. So very rude of you, Richard.
Yeah, I'll try not to do that in the future.
All right. So this is a graphical view of the inner solar system. And you got Jupiter's orbit is the outside orbit here. Here's the main asteroid belt, which is between Jupiter and Mars. And you see there's a lot of asteroids there. But you can see here's Jupiter, 60 degrees in front of and 60 degrees behind Jupiter. We see these clusters of asteroids. And these are the Trojan asteroids. Now, the asteroids aren't just locked in one position. They're actually kind of like orbiting around at that location, but they stay within that cluster. They just kind of orbit around the cluster. In fact, I've got a little animation here. It gives you an idea what I'm talking about. You see how the asteroids in the Trojan regions just sort of orbit around, but they stay either roughly 60 degrees, the central point is roughly 60 degrees ahead of or behind Jupiter. And this is where the Lucy mission is going. It will take off this coming October 16th, a week from today, and it will be on a 12-year mission. It will first fly around the sun a couple of times, getting gravity assists from the Earth to speed it up so that it can get out to the same distance as Jupiter is, out to the L4. It initially is going to go to the L4 Trojan cluster. It will spend some time out there and it'll arrive there, I believe, in 2027. It will spend some time out there visiting a couple of different Trojan asteroids. And then it will leave L4 and it will head on over to L5, arriving there in 2033 and visiting a couple of more. And I think I've got a diagram here to give you an idea of what I'm talking about. So it's going to take off from Earth. It's going to do a couple of orbits around the sun, each time passing the Earth, getting a little boost from the Earth to kind of speed it up and change its orbit. And eventually it's going to go out to the Trojan cluster region, visit a couple of asteroids out there, and then it'll swing back around, get another boost from the Earth, and head out to L5 and visit another, I think, 2 more asteroids in L5. So this is the Lucy mission, and this is what's going to launch next week, also on the same day as International Observe the Moon Day, October 16th. So I thought I'd just share that with you. You're probably going to hear something about this in the news. And when you do, you can say, oh, I know what that is because you heard it here first. All right?
Yeah, I have one other piece of spacecraft news.
Okay.
So, for years, everybody has been lamenting the impending end of the Hubble Space Telescope mission. Even though Hubble is still working, it's literally on its last leg. And we've talked a lot about how the James Webb Telescope is going to be the premier great telescope in space. But there's another one. And there's another one that passed its design review today, or it wasn't today, it was actually this week. And it's really the successor to the Hubble, and it's called the Nancy Grace Roman Space Telescope. And it is going to be launched in hopefully 2027, no later than 2027. And Nancy Grace Roman is considered the mother of the Hubble Space Telescope. She was very involved in that project. And this is a similar instrument. It is designed for the visual spectra. It has a much larger field of view. It's got 100 times the field of view of the Hubble. And so it's going to be doing large swaths of sky and gathering images and data about much larger regions of the sky. And it's also going to be looking at extrasolar planets. And basically taking over from where Hubble left off. And so I thought I'd mention that. You'll be hearing more about it as the years progress. It's kind of a little-known space telescope among the public right now, and but you'll be certainly hearing more about it.
All right. Well, now's a good time. If you have any questions you want to fire at us, that would be a good time to do it. We'll be glad to answer your questions if we can. If we can't, we'll make up something.
We'll make something up.
Yeah. We do have an event going on up here at the Chabot Space and Science Center. There's a wedding happening up here, and we've got a few people out on our observatory deck who are looking through our other telescopes. Fortunately, they're not being nearly as noisy as the crowd last week was, so it's much nicer.
Well, that reminds me of a question that came up earlier. Somebody was asking, can we ever do our virtual telescope program from the refractors? And there are some. It's technically possible that we could, but there are some real problems mechanically for us to do that. So, for instance, I'm imagining the length of the cables we would need to attach a camera to Rachel, our 20-inch refractor telescope, which is this immense swing arm. Right, the eyepiece literally swings from one side of the 40-foot dome to the other, and the swing on Nellie is much smaller. I'm able to use a standard 15-foot USB cable, and it never runs out of room. That wouldn't do much for Rachel. I suppose it would be easier to do it with Leia, which is a smaller refractor, but because of the smaller aperture, we wouldn't get anywhere near the amount of light, especially in live view, for this presentation. So I think there's a lot of technical challenges in trying to do that.
Yeah, probably the biggest one is neither of those telescopes is computer controlled.
No, that too.
So
you would have to watch us for half the program trying to find stuff.
Yeah,
that's really boring.
Yeah, when we're doing public viewing up here, we tend to point those telescopes at one object and leave it on that same object for most of the evening. And one of the reasons for that is that it is much more difficult to move the telescope from one object to another. And when you've got a whole line of 50 or 60 people waiting for you to move the telescope so that you can find the Ring Nebula, and you're doing it all manually, and you're having to literally look through the eyepiece of the finder scope and figure out where the Ring Nebula is, while there's 50 people tapping their foot wondering, when are you going to finally find it? It can get kind of awkward. So that's not probably not the best way to be doing a live stream
Yeah,
program.
using the refractors requires a real attention span. And whereas with Nellie, it's we're able to just jump from one object to another by pressing a button. And
Yeah, yeah. That's the easy part about operating this telescope. There's some other
yeah,
things that aren't so easy, but
true.
yeah. All right. So how are we doing on questions here? You seen anything?
Nothing new coming up on Facebook. Anything else on YouTube? If not,
No, no,
well,
I don't see anything on YouTube either.
well,
So
then, thank everybody here for joining us tonight, and I hope you had a good time. And please join us next week for the International Observe the Moon Night, or as I like to call it, International Howl at the Moon Night.
howl at the moon. Yeah. Yeah.
So we probably won't be doing any of that because we're going to have our friends from NASA with us, and I don't know if they'll appreciate it. All right. I
Okay.
think that's it. We'll see you.